about what does machine learning have to offer mathematics, a question which is on many of our minds. And I'm Nikhil Srivastav. I'm a senior scientist here at the Simons Institute. So I'll say a little bit about the institute. For those who aren't familiar, this is we're the leading international venue for collaborative research in theoretical computer science. And we were established in 2012 with a generous grant from the Simons Foundation, who continues to support us. And what we do is we bring together the world's leading researchers in theoretical computer science, as well as the next generation of researchers around thematic semester programs that focus on algorithmic issues, both inside computer science and in other areas of science, humanities, the social sciences. A big part of our mission is to make algorithmic thinking accessible and visible to a broad audience. And that's what this lecture series, theoretically speaking, is about. Its goal is to explain exciting discoveries and developments to a general audience. And in this context, I can't think of a better speaker than Jordan Ellenberg. So Jordan is the John D. MacArthur Professor of Mathematics at the University of Wisconsin-Madison, where he works on number theory and algebraic geometry, studying solutions to Diophantine equations using techniques from geometry. His work is highly influential. He's won many awards, including the Sloan Fellowship, the Guggenheim Fellowship, the Simons Fellowship, and a fellowship of the AMS. He's also one of the foremost writers of popular mathematics of our generation, having been compared to Lewis Carroll and Martin Gardner. His first book on mathematics, How Not to Be Wrong, was a New York Times and Sunday Times bestseller. I haven't read the book, but in preparing these remarks, I read Bill Gates' review of this book, and I immediately bought it. And one quote of Jordan stood out from that review. It is, "To do mathematics is to be at once touched by fire and bound by reason," which I loved. And then his second book, Shape, explains how geometry is at the root of many real-world phenomena, including elections, pandemics, and the stock market. And that's pretty much, that's most of what many of us spend our time thinking about these days. And more recently, he's done groundbreaking research on this type of question. So take it away, Jordan.
Thank you. Wait, I don't need that, right? Because I'm already, I think if I try to talk through both of those mics, that'll be a problem. Well, thanks so much. It's great to be back here. The Simons Institute is one of my favorite places. I've been here both as a researcher and as a science communicator in residence. And I guess today it's sort of a fun opportunity to sort of combine both of those things, because I'm to some extent going to talk about some research that I've been involved in, but also my goal today is, not so much to show off my own stuff, but to try to communicate some of the really interesting stuff that's happening at this interface between machine learning and pure mathematics. So let me start with a puzzle I like to start talks with, which is simply, what is this list of things? Okay, we all saw it. I'm not going to say anything about it right now. We're going to come back to it, but you've all seen this, and remember it. We'll return to it. The main thing we're going to talk about is stuff I learned while writing this paper. So you see my name kind of right in the middle, which, if you know sort of citation practices of computer science, means that I certainly was by no means the biggest contributor to this work. The people at the beginning and the end did the most. All these people on this list are folks who work for Google DeepMind, except for me. And one thing I want to talk about is, especially for the, I see a lot of you guys are students, right? I see a lot of people who look like students. Show me if you're a student. Okay, awesome, great. Okay, so many of you, if you're in this room, you're actually probably thinking about what you're gonna do, and maybe you're like, maybe I want to be in academia, maybe I want to be in an industry working in a place like DeepMind. So maybe one thing I'll try to convey today, especially for you guys, is kind of the interesting differences and commonalities between the two approaches to these kinds of problems that we see in these two very different kind of workspaces, and how I think that we can productively work together. But I'm going to start today trying to wrestle with some of these big questions about what is the proper relationship between machine learning and math. And I think we can only answer that by thinking of math as sort of one in an array of sort of more or less creative activities. So what do we have on this slide? We have on the upper left the opening page of a novel. Author, anyone? Any? Yes, okay. A great work by Anthony Trollope. Check him out if you get the chance. The Way We Live Now. On the upper right, we have a Go board. On the lower left, we have a problem of asking for the product of two rather large integers. Well, large for us, maybe not so large for the machine. And on the right, here's a paper I wrote. So this is kind of what we're supposed to be talking about today, right? Sort of like work in pure mathematics. So all four of these things like represent things that we might ask a human brain to do, right? Like write a novel, play a game, multiply two numbers, or write a mathematical paper. And so this gives us a range of things that we might also ask. How well can a machine do them, and what does it look like when a machine does it? So for instance, if we ask a machine, as I did just yesterday because I wanted to make this slide, to sort of write, if Anthony Trollope were still alive and like wrote a novel set at the Simons Institute, how would it start? I don't know, is this, should I read this aloud? Is this probably not readable for people in the back? I'll read the beginning. In the heart of Berkeley, where the air was perpetually tinged with the scent of eucalyptus and the hum of intellectual fervor, stood the illustrious Institute for Theoretical Computer Science. It was a place where minds as sharp as the Californian sun converged, each individual a node in a vast network of thought and innovation. I noticed they took Simon's name out of this, actually. That's kind of harsh. I didn't realize that they did that. But it's I only am noticing that now as I read it aloud. Okay, so what you should notice about this are two things. One, it's pretty bad. And two, maybe more importantly, it doesn't sound like Trollope at all. Now, I mean, there are things we could do to sort of try to maybe if I had, instead of just asking it to imitate Anthony Trollope, really given it sort of some big chunk of text. But if you have experience with these kind of systems, you're probably pretty familiar with this kind of aspect of automatic text generation. Okay, you could also ask, well, maybe it's here's an area where I think people would say that machine learning has done much better, right? And its ability to play Go. This is a picture of this sort of semi-despondent Lee Sedol, like getting whopped by AlphaGo in this sort of famous match, which was the end of human supremacy in Go. So here's what I would consider sort of a success for the method. I mean, this is also mathematics, right? And I just want to emphasize that here you see a piece of a machine doing mathematics, but in a way that maybe we sort of don't find threatening or surprising at all, a way that we're like quite used to, that we don't even think it's strange that this cognitive task, which a human could do, but at some length, probably very liable to make mistakes, is not at all difficult for a machine to do swiftly and perfectly. And then finally, you could ask, and this is kind of what we're going to talk about mostly today. Well, what about the project of doing research in pure mathematics? Is that like of those three things I just showed you, which is it like? And I chose those three things because I think pure math has aspects of all of those things. So I don't think there's a clear answer. I hope that the title of the talk being a question didn't make you guys think you were going to get an answer to the question by the end of the talk. Maybe I overpromised a little bit. But I would have called it what machine learning has to offer pure mathematics, period, if I were going to answer the question. I'm going to raise a lot of questions today. I'm going to give some of my own experiences, but it's still going to be a question at the end. Anyway, what are we looking at here? This is a wonderful piece of work by Dahmen, Holzel, and Lewis, where they took this paper that Dion and I wrote that I showed you in the last slide, and put it into the formal language lean. I'm not going to talk so much about formalization today, but I do want to mention it because it's a big part of the story. Math papers are mostly written in human languages, especially English, but a lot of other languages besides. But they're not written in formal languages like computer languages. And that's kind of changing. We're sort of figuring out like usable formal languages, which are actually computer readable for math proofs to be written in. There are large scale projects going on right now where people are trying to sort of take big complicated mathematical proofs and write them in this formal language so that they can be, for instance, checked by machine. This paper of mine was a rather short one, 6 pages. That's why this has already been done. And you sort of see like the sort of theorem statements. A theorem about cap sets, which we're going to talk about in a little bit. So this was not, I want to emphasize, this was not produced by a machine. This was produced by these 3 people whose names I put on the board above. But I put it up because maybe a lesson to be drawn from these 3 things is, where is machine learning strong? Where, like right now in 2024, is machine learning actually doing like a really great job of problems that we want? And I think I don't think this is too controversial what I'm going to say. I think that it does best when what you mean by success is kind of objective. There's no argument about it, and very easy and fast to check. So I think a good example of this is a game like Go, where it may be like a very hard problem to play Go well, but it's not hard to know who won, and it's not hard to know what the rules are. Those are very formalized and direct, and I think that's an arena where right now machines are doing very well. Whereas writing a novel that sounds like Trollope or writing a novel that's any good, there's not really an objective metric by which we can measure success. And even to the extent that we can sort of measure success at that goal, it's kind of like a slow, human, subjective process. And so a lot of the tools that we have to sort of like do very well, we don't have access to. And then maybe my second bullet point is a little bit more controversial, but I think it's something that a lot of people would say, that it's easier for it to do well if the thing it's trying to find is, in some sense, inside the bounds of stuff that already exists. So actually, because I see, again, a lot of students in the room, I love this metaphor, but how many of you guys know what the convex hull is? So yes, so I'm going to draw a picture. It's just such a great piece of mathematics that works well as a metaphor, like for lots of things in life, that I can't resist sort of saying what it is. I'm going to go back and forth some between slides and whiteboard through the course of this talk. So the convex hull, quite simply, is if you have a bunch of points, and we only have a 2-dimensional board here, so I'm going to write them in 2 dimensions, but this makes sense in any number of dimensions. The convex hull is what you get if you, what's the easiest? OK, as a pure mathematician, I would say it's the intersection of all the half planes that contain all the points. Those words may mean something to some of you and some not, but I can easily draw it. It means you sort of draw straight lines around the outside. There's a polygon, the sort of smallest convex polygon you can draw that contains everything, and it looks kind of like this. So these guys are on the convex hull. They're kind of the outliers, and these 3 other guys are sort of in the convex hull. So you can sort of imagine that if the thing you were trying to learn was in here, and you had all these data points, this is somehow in the zone delineated by the things you've already seen. Maybe you have some chance. Whereas if you were trying to sort of learn something out here, maybe you would be more surprised if the machine could get there. This is like outside the convex hull. So the question is, this is my little sort of mental picture of like which things machine learning does well at. And then the question is that what my job is like? Is that what being a pure mathematician is like? Is that what the process of doing research in math is like? And I think this is like a little bit of a controversial question. And I think I'll say this. I think outsiders to pure math are much more likely to think of the answer as being yes. In other words, like people who are not mathematicians are much more likely to think of the process of doing mathematics as something like the process of multiplying 2 large numbers, except like really hard. Like really big numbers, like bigger than we can imagine. I mean, that's I think some people's mental model. And I think we all know that doing research in pure math is not like that. On the other hand, we do have a story we tell ourselves, kind of handed down to us by the sort of early 20th century mathematicians who were sort of developing foundations and building mathematics on logic, that maybe what we are trying to do is develop these very formal arguments where we sort of have certain axioms and we're allowed to derive facts from those axioms by certain rules. So maybe not quite like multiplying 2 numbers, but maybe more like Go. Maybe more like where there's rules of the game and they're complicated but we're bound to them. And that's the thing that we're doing. Ken is shaking his head very grumpily. I don't believe it either, but it is a take that some people have. So I think math is sort of uneasily poised between having that aspect, and yet I think any practitioner of math would say that somehow does not feel like all that it is. And let me sort of, in this respect, well, let me tell a rather famous thought experiment that people talk about all the time. Let me actually go back one slide. So here again is what a formal theorem statement looks like. It looks a little bit different from the theorem statements in English that we write in our papers. And in this, if you go to sort of these folks' GitHub page and look, you'll see not only these theorem statements, but a formal proof of these statements, which is like a much longer string of lean code that looks a lot like this. Okay, now imagine with me the following world. Take a very famous problem in mathematics that all number theorists like me care about. Let's say the Riemann hypothesis. Very old conjecture. We all believe it's true. We don't know any proof. You can, it would certainly be, I think probably even with lean as it is, I think you could write the statement of the Riemann hypothesis in this formal language. I'm not totally sure because they're still sort of working on the complex analysis, but let's posit that you could. Now imagine some universe in which a machine is able to generate a formal proof of the Riemann hypothesis. This is very long, billions and billions of tokens, but checkable by machine, so you would be absolutely certain, at least insofar as you were certain of the machine's operation, that this thing, which we all have believed to be true but had no proof, now we know it's true, and now there's a proof. What would happen? What would be the meaning of this? Okay, I'm going to say what I think. It's a little bit, I mean, not every mathematician would agree with me about this. I would say that means nothing, and nothing has been gained, and I absolutely do not care. Why? Because, first of all, I already know the Riemann hypothesis is true. Come on, it's obviously true. It's like, I feel like it would, I mean, that's not the issue. And moreover, I would not understand anything about the Riemann hypothesis that I didn't understand before, because this proof would be like non-human readable and would be sort of no more than a certificate. So the claim I'm making here is kind of a strong one, and not every mathematician would agree with it, but I think that probably, I almost want to do a show of hands for the working mathematicians in the room. Does anybody want to like go against me on this? Okay, a lot of people, good. I'm going to say, I do not think that mathematics is primarily about figuring out what's true and what's false. But that's...
What you said is much more than just whether it's true or false. You said that the machine was able to show it. That's a lot more than just true or false.
Okay, say more.
Well, that's it. I mean, that's...
Well, now you have an artifact that you can poke at and look. Maybe there's something we can look for in here for more information.
Okay, but in my story, we can't do that. In my story, it's like a billion tokens of like unreadable code that we can draw. So you're absolutely right that you can imagine a world in which that wasn't the case. But I'm telling the story, so I get to imagine how it is in my story. Okay, yeah.
Do you have similar misgivings about the proof of four-color theorem?
I don't, and I'll say why. Let me sort of, for those who don't know, let me sort of tell the story. This is one of the first machine-assisted proofs in which Apple and Haken reduced this famous problem of can every map be colored by four colors to a rather large finite computation, which the machine then did. But the reason that I don't think of it the same way is that in my mind, what they proved was the reduction to the finite computation. That's the proof. And then the finite computation I care about a little less. That turned out to be wrong. Like, okay, I don't care. So there's some map that can't be colored, whatever. Yeah.
Well, I think it's important in the sense that if you want to build new mathematics on top of it, you better be sure that the foundation is true, right? And if you get that check mark, you can leave it aside and do your new math. Without that, you might build your whole thoughts on just mud.
You might, but let me point out that mathematics has been very successful by building on foundations that turned out to be rather muddy, and that somehow it came out okay anyway. Even though, you know, we developed algebraic geometry, and now we like look back and we're like, okay, actually, like a lot of that stuff wasn't proved carefully. Like some of the statements were wrong, but it was okay. We understood what was going on, and so we somehow didn't like mess up too badly because of that. Okay, boy, we could do like an hour of this, and it would probably be fun. So let me, all right, proof by authority. I'm going to quote Thurston. No, but this is from a very, very famous essay, which Ben is always telling me I should get past this essay, but it's still great. I mean, so he wrote, and this is from 1994, so this is from a long time ago, certainly before the current boom in formalization of mathematics. But already, I mean, this question has been a live one for all of the history of mathematics and its philosophy. And so here too, what Thurston is saying is, it's not really a question of how many theorems can we prove, and it's not really a question of how much can we prove is true and how much can we prove is false. It's, do we understand stuff we didn't understand before? And in that respect, thinking of it that way, then the proof of a theorem becomes something like a benchmark, like a way of being like, okay, I must have understood this better. It's not an illusion. I'm not fooling myself into thinking I understood something because my understanding led me to this proof that mathematicians before us were not able to get. Yeah.
I agree with you, by the way, but we have the same qualms.
Thank you for agreeing with it before you understood it. Okay, carry on.
Instead of a machine, it's just 5 people in the world and nobody else can understand.
So, well, then we could say how many people are meant. Right, I mean, somehow, like, I will say, at the risk of like really taking us on a detour, I mean, we are in the midst of it, not in the midst, we're sort of past the midst of a situation in number theory in which a famous conjecture was asserted to be solved by a small group of people who their belief is, unfortunately, nobody other than us 5 understands this correct proof of this theorem. And I think most people, including me, feel like that's because there's not a proof there. But I mean, that does happen, right? In the world in which they're correct, then it would be like that. And in some sense, I would think, if that were true, their failure to write a proof that anyone outside those 5 people could understand, I think would sort of constitute like a failure to develop mathematics, because like nothing would come from it. So, okay, we're gonna have kind of a shift of course now, because this is sort of, I wanted to sort of lay down the philosophical beginnings, but I do want to sort of talk a little bit about actual machine progress in pure mathematics right now. But to do that, I want us to do a little bit of kind of interactive work, because I think one of the big problems with communicating about this field is it can seem a little bit like magic, and to be honest, there's like a lot of people whose incentive is to make it seem like magic. And I have a very non-magical view of like what machine learning actually is. So if it's okay, like we're gonna do a little exercise, and I'm gonna ask something. We're gonna do a little like real-time machine learning so we can see how it goes. So here's what we're going to do. We're going to play a game that Claude Shannon invented in the 1940s, the very beginning of the subject we now call information theory, machine learning, and artificial intelligence, what have you. And the game is going to require all of you to have access to some reservoir of text. So if you have a book in front of you, or I never say this when I'm giving talks, this is the only time I'll say it, if you can take out your phone and like go to some place where there's some like large body of text. Because I want everybody to be in on this. And let me tell you how the game is going to go. Oh, I might need, do I have an eraser here? Oh, that's what this is. Okay. So Shannon was very interested in automated production of text. Well, he was interested in a lot of stuff, but this was something he writes about in his famous 1948 paper. I said you could take out your phone, not that you could like play music on your phone. Okay. So his idea, and I'm going to start with the letters ST, and we're going to make some English text. And the way we're going to do this is the following. We want to know what the next letter is supposed to be. And the way we're going to think about that is like, well, in English, the letters ST could be followed by any number of letters. It could be followed by an A, maybe not very likely a B or a C. Maybe it was like Saint Croix, the island in the Caribbean. It might be an STC, a little bit rare. It could be followed by like a lot of different things, but some are more frequent than others. And if you want to sort of estimate what's likely to follow an ST, the typical way we do things in statistics is to sample, right? So you guys are going to be my samplers. And everybody right now is going to look through your text until you find the letters S followed by T. And when you do, first person, tell me what letter or space follows it. Okay. E, okay. So again, space is okay. If now we're going to do TE. If that's the end of a word, just tell me space.
Oh, S.
I heard E first. Okay. Double E.
A.
A, really? Okay.
S.
RS. Anybody got an RS?
Space.
Space. Okay. Good. We'll start a new word. Oh, so now let me explain what happens now. We have S space, which means you need to look for a word that ends with an S and then the first letter of the next word, because it's right? C. Okay, I heard C. Okay, so now we have space C, so you need to find a word that starts with C, and what's the next letter?
Oh.
Okay, I heard O.
L.
Okay, OL.
A.
Space.
Okay. So A space, so we need to find a word that ends with A, and what's the first letter?
P.
Okay.
A. S.
AS?
Space.
Okay. All right, we can stop here. I think you see how this is going. So, okay, so Steers coalesce, which somehow, like, this process, you can see, it generates something which is, it has something in common with English text without actually being English text, right? This rather simple mechanical method, it does tend to, if you like, know something, and we're going to be doing a lot of anthropomorphic words with scare quotes in them in this talk, so that will be the first, about how English works and which letters like to follow other letters. And we could also have done this, I did this with what are called trigrams with you guys, which are sort of sets of 3 letters, so like ST blank. We could also have done it with bigrams, where I just gave you one letter and you're like, what's the next letter? Or I could have done it with longer strings, like pentagrams, where if we had STEE, you would look for an STEE in your text, and like that would take. We don't do that in the room because it takes a little bit longer, but on a machine, it's not so hard to do. And if you do it with longer strings, what happens is you get something that captures more of the features of English. But you know, actually, can anybody guess what would happen? Has anybody ever done something like this? Yeah.
Closer to being reproducible English, I think.
Yeah, what might happen is that if you were the person who found STEE, maybe because the word steep was in your paper, then we would have TEEP. And when I was saying find a TEEP, that might be you too. I might just be calling on you again and again and again because we would get trapped reproducing some text that you happened to have. So the longer the strings, the better the fidelity of sort of capturing features, but also the greater the risk of reproducing something in the data you started with. Oh, here's, by the way, here's the famous sentence from Shannon's paper. In no lat way cracked it for bears grossid, pondenome of demonsters of the reptigan is radioactina of cray. Love this. So this is something that Shannon did. And of course, when he did it, he was by himself. So he would do it by like picking books off his shelf in his library and doing the exercise we just did. But we can do it a lot faster with this many people. But it's essentially the exact same exercise. And this was a sort of famous thing that he did with trigrams from his library, sort of demonstrating that you can sort of capture certain features of English. So looking at this, I'm realizing there's a slide that I don't have, which is like a little bit sad because I just sort of changed up my slides for this talk. But I do want to answer the puzzle that I started with at the beginning. So let me kind of go, I'm going to, sorry to click, but I'm going to go all the way back. I think I don't have it. Let me just quickly look forward. Oh, no, I do have it. Oh, good. Okay. Right. So I do want to emphasize there's one feature that's pretty important of modern machine learning techniques, because I like to sort of say, like, okay, I just showed you how machine learning works. But you probably know that modern machine learning wasn't invented in 1948. So something must have happened between then and now, right? So I will comment that what if instead of starting with ST, what if I'd started with WQ? What would have happened? Yeah, you guys all would have sat here for a long time. I actually looked this up, and according to at least one site, which I don't know if it's that reputable, there's only 7 bigrams that don't occur in an English word, and WQ is one of them. Oh, wow. How old are you, man? Even I don't use it. If it's not in Emacs, I don't know what. Okay. Oh, I see what happened. Okay, I put these somehow slightly got a little bit out of order. Okay, I'm going to skip over this really fast. So, so even though we would have gotten stuck and the process I just told you would not work, there's still kind of a right answer, right? Like, what would you put next? Yeah, you'd put you, right? Because you somehow know something about English that like this protocol doesn't know. And you wouldn't get stuck. You would just be like, okay, maybe I'm from Wisconsin, so I'll say maybe there was like a cow quake, like a lot of cows were running by, so many that it caused the earth to shake. I mean, you're trying to think of some, in any context in which you had a WQ, probably it would be followed by a U. So in some sense, so I have a slide for this. So even though the game doesn't work, you should still say U. And so in some sense, what we actually want to do is say, in real life, when we're producing texts like the sort of fake Anthony Trollope text I just showed you, it's not sort of, it doesn't have like half of a sentence and then find that exact sentence somewhere in its text. There's some notion of similarity. There's some notion of likeness where we can say, well, WQ is not a string I found, but I found a lot of other strings like it that ended with the same character. And in every single one of them, I said U. So I should probably do what I did in similar situations. And there, of course, is a huge amount of art and a huge amount of technique that I'm mostly not going to talk about today. But now, good. Okay, now I can answer the puzzle. What was that list I gave you at the beginning? And what that was text generated by the trigram method we all just did in the room from a list of names given to babies in the United States the year of my birth, 1971. So Kendi, Jean, Abby, Fleury, Melia, Jean, Starlo, Kaming, and Batila were generated by that process. And you could do the same thing. Actually, there's a great, the Social Security Administration, for some reason, has incredibly clean machine-readable data about baby names given in the United States in every state and every year since 1913. Very fun to play with. So you can just do this. You can do this for babies born in 2017, and you get Anaki, Emily, Chan, Jaylee, Elif, Branchy, Navio, Corby, Luxton, Naftaline, Rayerson, and Alana. And these are like playground plausible names, are they not? Yeah, maybe. Whereas if you do it with 1917, the names given in 1917, you get Venzi, Adele, Alwood, Walter. There's a real one, right, Walter? So you do see some reproduction of actual things in the data set. Wanda, Liadi, Catherine, Fran, Ernest, Carla, Cecilia, and Oberta. And I just think this is really worth looking at for a second because, oh, and also I guess here I even did like, I showed you what it looks like if you use bigrams and pentagrams instead. And with bigrams, you get kind of somehow wilder names that are farther from real English naming practices, like Madrahadria. I think that's my favorite one. There's something a little bit Games of Thrones-y about what you get if you just use the bigrams. And then with pentagrams, you really start to see reproductions of names that are in the data set or things that are very close, right? You see like real names like Adam and Susan, and then names that are so like Contrina that are like, or Chris-Anne, they're like pretty close. So I just want to emphasize, because I think it's like worth noting that what we did here was extremely simple. It does not use any modern machine learning techniques or anything, but already it somehow does this thing that we're amazed that generative AI can do, which is it sort of captures certain features of a body of text that exists. It really has learned something about the style of name giving in these different times. Ooh, did I do that? I think you did that. Okay. Now, with that in mind, we're going to come back to this. This is a public lecture, so I'm going to have like a pretty limited amount of like math per se in this talk. But here it comes, like a little bit, because I do want to sort of talk about this CAPSAT problem, which I sort of showed you the paper of, and which is the problem that the DeepMind folks and I sort of set out to work on. So what is a CAPSAT? A CAPSAT, oh my God, I wrote 013, but I mean 012. Sorry about that. I guess it doesn't actually matter, but like a normal person would say 012, so that's what I'm going to say. So I have a set of length n strings, and by a line, I mean this kind of funny condition. And don't worry, I know this is kind of hard to parse in English words, but we're going to write an example on the board in a second. Is a set of 3 strings which, with respect to each position, either has all the digits different or all the digits the same. And then a CAPSAT is a set of strings in which no 3 form a line. So let's think about this when n equals 2. because then there's not so many strings, right? And I'm going to write them all down. So length 2 strings. OK, we can erase our generative AI text now. I'm going to write them like this. 0, 1. Sorry, let me write 0, 0, 0, 1, 0, 2, 1, 0, 1, 1. Can you guys read this? Should I use a different marker maybe? It's a little light, right? OK, let's try this one. This is a little bit better. 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. OK, so these are the 9 length 2 strings. And I have some notion of what it means for 3 strings to form a line. Remember what it means. It means that with respect to each coordinate, the numbers are either all the same or all different. So let me draw one. Oh, you guys are stepping on my punchlines. But I did want to say, literally somebody came in here who has the game set on the back of their shirt. I think it's you. Is that right? OK, can you show everybody your shirt for a second? So there is a card game called Set, which some of you may be familiar with. And most people, certainly me included, who work on this math problem learned about it from this card game. But it turns out to be actually like a rather old problem tied into like large parts of what's called additive number theory. But for the moment, but again, we only have a certain amount of time together. I want to talk about DeepMind stuff. I want to talk about Anthony Trollope. So we're not going to do the whole part where we talk about the card game Set, much as I like it. We can talk after for the fans. OK, so I'm going to give you an example of a line. There's one right here. These 3, because the first coordinates are all different, and the second coordinates are all the same. OK, so that's an example of a line. And look, it looks like a line. So that's good. Here's another one, 0, 0, 1, 1, 1, 2. Those form a line because in this case, each coordinate they're all different. So the question is, and again, OK, this is like the second and I think last audience participation portion. But to get a sense of what problem we're asking here, just take like literally a minute or two and say, how big is the largest cap set? How many of these 9 strings can you select in such a way that no 3 of them form a line? OK, no raising your fingers yet. I literally want to give everybody a minute to think about it. I'll watch the clock because I don't have my phone out with an alarm. So I'll give you guys a minute and then we'll. If you have paper, you can use it. I find it hard to sort of do this in my mind, but. OK. Yeah, so this is very, OK, we're at the end of our time, and Lisa's question is a very good one. This is indeed exactly like the question of how many cards can you have out in this card game set in such a way that there's no legal play. So this funny rule that I wrote down on the board is also very familiar. It's also the rule of the card game. Well, first of all, OK, what did we get? How many did you guys get? Now you can like hold up your fingers or. OK, I see. OK, good. I see a lot of 4. And 4 is indeed how many you can get. A lot of times people say like 5 or 6. Maybe you were thinking it, but were like too scared to say it. And if you say 5 or 6, it's probably because, and I sort of sneakily didn't point this out, it might be because you forgot that this is a line. these ones that kind of go off the edge of the page and like come back. But this set of three things also forms a line, although it doesn't quite look like it on the square that I drew, because they also have, with respect to both coordinates, all three things different. So actually, there's a nice way. I mean, one way I like to write this set of 4 is just to sort of cut out the top left corner of this diagram. I could have done like any of the 4 corners. In other words, it's rather easy to say that if you only use 2 of the digits, if you only use, say, 0 and 1, it's sort of a fun exercise to show that what you get is a cap set. And so for any n, you have a cap set of size 2 to the n generated in that way. And actually, when I first learned about this problem, I was like, oh, that's cool. So like, let's prove this theorem that the largest cap set has size 2 to the n. And I worked on it for a while, and I couldn't do it, and it would really hurt my self-esteem. But then my self-esteem got better because I found out that's completely not true. See, it's much better if you can't prove something. It's much better if it's because it's false than because you just weren't clever enough to finish up. In fact, not only is it false, it's already false for n equals 3. So really, for the students, don't do induction on just 2 cases. That doesn't work. You should always check at least 3. So in any event, I will just say, again, in a different kind of talk, we would just have like a whole long talk about this wonderful problem, what it has to do with sets of integers without 3-term arithmetic progressions, the sort of famous result for which Roth won the Fields Medal back in the 1930s. I mean, all kinds of stuff. But we're not going to do any of that today, although I'm happy to talk about it after, sort of because I don't want to sort of give a pure math talk. I want to sort of talk about how this problem is approached by a machine. And let me say what you might do traditionally, because there's certainly like a long history of like using machines to try to get some purchase on combinatorial problems. You might just sort of try in some inventive way to sort of search the space of all subsets of the 3 to the n string. And when I say search, what do I mean? Do I mean look at them all? Come on, you guys are computer scientists. Is that what I mean? Why not? Too many, right? 2 to the 3 to the n subsets. No chance, no chance. So search means like, maybe you have sort of some function and you threshold it, and where the function is above 1, that's your set, and you sort of move around in some space of functions. So you do something, there's things you could try to do. And the output, even if you got a good solution, would be sort of some long list of strings. And what I want to emphasize is that even if you found a good list of strings, it would a little bit have that Riemann hypothesis problem. Like you would look at it and you'd be like, okay, that worked, but like, what did I learn from it? So the folks at DeepMind, and I want to emphasize this whole protocol was like their idea. I wish I thought of it. It was pretty cool. They were like, what if we do something totally different? Instead of searching directly for the set, search for a program that outputs the set. So we're going to search the space of literal computer programs, like Python programs, instead of searching the space of sets. Now, we're going to do it. That's going to be on my next slide. No, these guys are very clever. Okay, I mean, but I just want to emphasize that this does seem like a bizarre thing to try to do, or at least that's how it seems to me. And let me now, on this one slide, I'm going to have an incredibly reductive cartoon of how this works. And maybe we'll spend some time on this because, like, in some sense, this is the main idea right here. And then I'm going to talk about what I learned from it and my thoughts about where we go from here. So here's the cartoon of this protocol called Fun Search. You start with 1 million programs. Where do you get them? Doesn't matter. They can be like random. Okay, do I like literally mean random? Like obviously I don't mean like random strings of characters because you would put them in Python and they wouldn't run. There's sort of some skeleton that guarantees that the program actually does output some subset of the 3 to the n vectors. But beyond that, basically nothing. And then you run each of these 1 million programs, and you say, how well did it do? The set that it outputted, was it a cap set, or did it have lines in it? Hopefully, and then maybe you sort of sieve down to the ones that actually give you a cap set, and then of the cap sets it gave you, which ones were the biggest? So that, I think you'll agree, is pretty fast, right? There's no exponential problem here, because you only have 1 million programs. That's much smaller than 2 to the 3 to the n. Right, but that's fast. Because, okay, good. Why is that fast? Because you don't have to check anything that's of size 2 to the 3 to the n. You just have to say the set that it makes, which has some size, you have to check all 3 element subsets of that to see if there's a line, and that's polynomial. So that's much, much, much faster. So this is a, in some sense, this is the kind of problem that machine learning is best at, where maybe finding the thing exhaustively would be very expensive and hard, but once you have it, checking it is much, much faster. So this step is fast and it's objective. But by the way, there's no machine learning yet, right? So where is it? So then you say, okay, I'm going to pick like the best, whatever it may be, like 0.01% of performers, and now I'm down to 100 programs. And then you have, or DeepMind has, like some large language model, which is trained on lots and lots of Python code. And they say, okay, I have these 100 programs. Now give me 1 million more that are like those. Right? This is exactly, if you've used a large language model, this is exactly what they do. You give it a prompt, and you say, continue this. Give me more like this. And then you just go around and around like this. Do we agree this is like a very weird idea for a thing to do? And yet it works pretty well. Before you even go on, I want to emphasize, I think one thing I find surprising about this is that the things I did before thinking about machine learning for math, you were really somehow using the machine learning step was optimizing. You were saying, like, I'm trying to take some function and it wants to achieve a goal, and I sort of move the function in a certain way and sort of check whether it achieves the goal. And that's where the machine learning step was happening. Here, somehow, you don't tell the large, I mean, I don't know what it means to tell, but the large language model sort of isn't, in some sense, trying to make these programs better at generating CAPSATs. All it's trying to do is do similarity, generating programs that are like the programs you gave it. In some sense, the optimization step is all here, and that has nothing to do with the large language model at all, or even anything that we would call machine learning. So this I think, is a quite interesting way to do things. And now I'm going to sort of give some observations about what I learned from this project. And the first thing is simply that so that's a great question. But I would say it's not optimization that's related to the CAPSAT problem. It's optimization related to how well can we produce programs that are like, yes. Optimizing. No, absolutely. It's optimizing something, just not something specific to this problem. So let me just comment that again, sort of to my surprise, this mechanism allows you to match the largest known n-dimensional CAPSATs for n 1 through 7. And actually, dimension 8 finds one that's like a little bigger. And actually, I think I'll show you this program for what it's worth. So I'm going to say something about, I mean, I don't know how many of you guys like to read Python. So first of all, when you look at it, this is what machine-generated code looks like. I think it looks something like human-generated code. I think it also looks a little bit weird in certain ways. Let me say something really weird about this protocol, which I did not put on the cartoon, which is that, as I said, you do have to sort of prescribe something about the nature of the program in order to get it to work. I mean, you don't want a program that just like prints out like hello world 500 times. Like, you want a program that generates like a subset of vectors. But even that is like too broad. So they have a very, very restrictive skeleton. And these are the kind of programs that in the end fun search is searching. And this is, again, is a moment where it's going to get like a tiny bit mathy, but I do want to make this point for the people in the room who work on this kind of thing. It basically assigns each vector a score, and then it adds vectors to your set in order of their scores. Except that it checks each one, am I allowed to add this, or would it make a line? And if it would make a line, I don't add it. I skip to the next one. By a vector, I mean a card, yes. But it's basically like lining up all the cards in order and saying, I'm adding each one it's legal to add until I can't add anymore. Yeah, that's about where it craps out in terms of. But I just want to emphasize what a strange way that is to approach this problem, because a human working on this problem would somehow try to be strategic, right? If you were sort of laying down more strings or more cards, you would say, let me try to lay one down. Let me like kind of look ahead a little bit and sort of try to lay one down in a way that's not going to sort of limit my further options. I mean, this is like, imagine if you wrote a chess engine and the way you wrote it were, I'm just going to give every move a numerical score without reference to the state of the board. And then at each play, I'm going to pick the highest scoring move that is legal to play in this situation. Like, you wouldn't believe that you could actually write an effective chess playing machine in this way. So to me, it's actually quite surprising that this extremely restrictive class of functions gets pretty good performance, and they were not able to get better performance with what I would consider a sort of more human-like or more reasonably strategic class of functions that you would think would do better. So I don't know what to make of this, but it was like something quite striking to me, and I wanted to sort of say it. So that being said, that's my intro to saying, if you look at this slide, what it's actually doing is defining a function called priority, and that's the score. So it's sort of assigning a score to each vector, and it's doing it in this kind of funny way where it's like, I guess I like it when the first coordinate is the same as the last coordinate. I'll multiply the score by 1.5 if that's what I get. And I like it when the second coordinate is the same as the penultimate coordinate, et cetera, et cetera. And the programs generally look kind of like this. There's things that it likes and things that it doesn't like, and it multiplies the score by numbers bigger than 1 sometimes and smaller than 1 other times. Sometimes it adds or subtracts something. It's not clear how it's like picking these numbers, but that's kind of what it tends to do.
Does this correspond to the conceptual idea?
Oh, no, that's very a philosophical question. Does it correspond to a conceptual idea?
Or DeepMind, like, could you extract some mathematical insight from it?
So that's the goal. And I'll say something about, I'm going to come back to this code in a second and say something about that. But let me quickly sort of say some more observations from a machine learning perspective. Oh, but you were raising your hand earlier. Sorry, let me ask.
How can you generate enough difference between that million programs that you have?
So, okay, I didn't put this in the cartoon, but this is like part of the general area called genetic algorithms. And so one thing they do is I drew it as if it was just like one big blob, but actually they have like a bunch of different islands that are evolving separately. And they actually kind of do a lot to ensure kind of diversity of programs and like not have it all sort of settle on one thing and not change. So that actually does require some technique that I'm not telling you about, if that's okay. Okay, so to emphasize, one of the main things we know that is problematic about large language models is that they hallucinate. They just sort of say things that's not true. One of the really nice things about this protocol is it completely eliminates that problem, because if the large language model produces something that doesn't make a cap set, we just throw it out at the evaluation stage. And the evaluation stage does not involve an LLM. So this very neatly kind of solves what I consider, what's generally considered like one of the sort of main drawbacks of using large language models to actually do anything. And another one, and this sort of speaks to the question that Nikhil asked, is that unlike a long list of strings, and in fact, the last time I was here as a science communicator, it was for this workshop last summer about interpretability in machine learning. And I remember the very first slide of the very first talk. Oh my God, I forgot this guy's name. The guy from Carnegie Mellon. You know who I'm talking about? Anyway, this very first slide was like, nobody knows what the hell interpretability is in machine learning, and that was true based on, but interpretability, we sort of know when we see it. It means that hopefully we can learn something from the output, which maybe from a string of zeros, ones, and 2 we can't, but from a program, just as you say, we can kind of look at it and sort of try to learn something from what it's doing. And I'm going to say something about that at the end. So finally, let me make this point, that there is something very fundamental to the way that humans think about this problem that at the moment fun search seems to not do, which is that, as human mathematicians, we sort of know that we sort of try to build up solutions to larger problems from smaller solutions. And in this problem, in some sense, this solution of size 2 to the n that I told you, you can think of it as saying, well, when n equals 1, 0, 1 is a cap set, and I can just put together n copies of that to make 2 to the n, and sort of that's what we do. That's very natural for us. Probably any human who works in this problem sort of comes up with that. And fun search somehow doesn't seem to be able to compose, or it doesn't have the idea of composing smaller solutions into larger ones. I will say, this is a good example. Wait, so Nikhil told me I'm supposed to like talk. I can talk till about 45, and then we have questions till 7. Is that the good slot? Okay, good. We're in a good place. So I will just, maybe I'll go back to this code for 1 second because I think I don't have another slide of it. To say that if you really squint at this, for those who like to squint at Python code, you can kind of convince yourself that maybe this is sort of trying to, this particular code is trained on n equals 8. It's the one that gives you the sort of biggest solution. You can kind of convince yourself that maybe it's thinking of this 8-dimensional space as 4 2-dimensional spaces glued together. Because maybe it's saying, well, there's some relation between spot 1 and spot -1, and that's 1 2-dimensional space. And there's some relation between spot 2 and spot -2. You don't want to fool yourself into thinking the machine's doing something that it's not, especially since when you sort of know what it's supposed to be coming up with. But there's at least some argument that maybe it's kind of there. But it certainly doesn't do anything like what we would do. So let me kind of summarize where we are with this. So what the results of this paper show that LLMs can do using this protocol is you can actually get it to produce a program which gives good solutions to a particular math problem. In some cases, although certainly not all, better than what humans have been able to come up with, even humans who have like worked on this pretty hard. So that's pretty cool, and that was like one of the goals of the project. However, here's what would be like something incredible, which I thought was not going to happen, and indeed it did not. I mean, remember, when I said, I sort of hit it a little bit, but in this cartoon, we sort of trained the program and sort of generated a million, sieved it down to 100, generated a million more. That was always for one fixed value of n. So the one I showed you was trained on n equals 8. And it got pretty good at making programs that made big cap sets for n equals 8. So what might you dream? One reason that this protocol is good is you're like, oh, well, now that the program works, let me just go to the top of the program and change n equals 8 to n equals 9 and see how I do. Well, how do you think you do? Pretty bad. I mean, you could hope, but no, indeed, the performance falls off extremely fast. It does very well in the thing it's trained on and no more. And then you can do other kinds of stuff, right? I was like, well, what if we trained it on like, 6, 7, 8, and 9? And then maybe it'll learn something that sort of generalizes a little better. Nope, it still totally falls off once you get past like those exact values of n that you trained on. So this is what's called the generalization problem. It's pretty hard. And so it just doesn't do that, at least as of now. It does not produce programs that work off the shelf for problems other than the exact problem that you trained on. But there is an intermediate goal, which is where I think the most interesting gains are to be had. And this, again, sort of speaks to Nikhil got me a little ahead because this is sort of the exact question you asked. What I do think is much more reasonable, and I'm going to is maybe not produce a program that actually works for n other than the ones you trained on, but maybe you can produce a program that when we read, we can sort of, it gives us an idea for something to do. Maybe the program doesn't do it, but we can do it in a way that we wouldn't have thought to do without having looked at this program and figured out what it was doing for the specific n it was trained on. So I'll say in this problem, how far do we get with that goal? I would say staring at some of this code and trying to figure out what it's trying to do. And I want to emphasize, by the way, that you do, or at least I do, looking at this machine-generated code, you do have a feeling that it's trying to do something. You do have a feeling that it's trying to do something that it can't quite articulate. It doesn't matter to me whether that's an illusion or not. All that matters to me is, like, am I getting some good ideas from it? So I would say in this problem, I did not get any ideas that enabled me to sort of generate new best possible cap sets for largest n, or else you would be hearing about that. But it gave me ideas that I thought were promising enough that I probably spent like a week thinking about them. And that's already pretty good, because I've thought about this problem a lot, as you saw, like I've written papers about it before. So I feel like if it's giving me ideas that don't immediately seem useless and that I spend a week trying to make them work and they don't work, that's already pretty good. Like that already makes me feel like, okay, something is going on here that's potentially useful. But I do want to emphasize, so I hope what I'm showing you here, by the way, is we started with these kind of fantasy stories about like, what if the machine produces a billion-bit proof of the Riemann hypothesis. Part of what I'm trying to tell you guys is that I think, like, at least in 2024 and maybe forever, in some sense, the way this is going to work is not you just ask the machine to do something and it does it for you. It's things like this where we're sort of iteratively collaborating and using the machine as a tool. So in particular, given that we can't even do this, I'm somehow not so concerned about these even harder tasks of eating all humans, or from my perspective, even worse, like sort of rendering our jobs as pure mathematicians obsolete. So because those would be even past this goal of writing a program that works for all n. So maybe let me close with one story that I think is like kind of relevant to the difference between academia and industry, again, sort of for the students who are sort of thinking about their future lives. I thought it was pretty interesting. So there's another problem, which is not part of the main paper. It's in the supplementary material that we talked about. Some of you may know it, some of you may not. It's a problem of computing the Shannon capacity of graphs. Same Shannon we were talking about before, by the way. So no need for me to define this if you don't know it. Let's just say it's a quantity that is famously hard to compute. We can't even compute it for polygons of size larger than 5. The computation of this capacity for the pentagon was this sort of like famous theorem of Lovász that it's the square root of 5. And for the 7gon, we don't even know. So we were like, well, this seems like a good kind of combinatorial problem. It has, thanks to this very good insight of Eric Naslund, that it's similar to the CAPSET problem, which can also be thought of as a capacity problem. So we tried this for various small graphs. And what you're seeing is a program that did a pretty good job of giving bounds on capacity, not bounds that were better than what were known, but sort of the best one it found for the 9 cycle, like what is it called? A nonagon. And what I want you to notice is that this program is really short compared to the ones that I showed you before for CAPSET, and actually compared to other programs that we're just generating for this problem. So I definitely was like, well, let me try to figure out like what this program is doing and why it's working pretty well on this problem. And it took me like a while, but actually I really did start to see, oh, I sort of get what this strategy is. It uses weird commands, right? Do you guys, I had to look this up. Do you guys know what this is? It's probably too hard to see, but like this double less than sign I. Who's Python enough to know what that does? Yeah, sort of. So in my world, I would just write times 2 to the I, but it's like shifting I binary digits over. So this is doing some kind of sum involving powers of 2. And when I really thought about this, I was like, oh my God, I actually see what this strategy is, what it's doing for 9, and like how you could apply it for all n to get sort of some lower bound. And I was very excited. But then I was like, this is too good. It's too simple. Like this has to exist already. And then indeed, once I knew what to look for, then I found it in this paper by Hales, written in 1972. And now you see something interesting, because I will say, I worry this is going to sound critical, but it's not. It's just like a difference. The DeepMind people were completely like, OK, well, that was another failure, because like, this was already known in 1972. To me, this was a grand success, because I think it's amazing that, in fact, by looking at this machine-generated code, I was able to have an idea, which admittedly was in the literature from 1972, but which I definitely didn't know and hadn't thought of. And this, to me, is like a proof of concept that you really can use these machines to kindle ideas in a human mind that do exactly what Thurston wanted, to increase our understanding of the problem. And it made me feel like, OK, this time it was something that was written in 1972, but it seems very likely that we will get it running to the point where we're really like seeing or generating, or in collaboration with the machine, producing ideas that are novel. So I'm just going to close with this picture. This is the Rind papyrus. I don't know if people have seen it. You're looking at a computation of pi to about almost 2 digits. I think it's sort of estimation of pi that's around 3.16. I just put this up to emphasize, I love this stuff. I'm really excited about it. I like to go around and talk about it. But at the same time, I think that a lot of the discourse around machine learning really treats it as a discontinuity, or even like a singularity. To me, that's not how it looks from the inside. The history of mathematics is filled with technology aiding us, finding new ways to use machines to do certain parts of the work and to aid us in doing the work we want to do, which is understanding stuff better. When that happens, it does sometimes become the case that things that were once math become merely computation, right? So like right now, if you're a mathematician and you compute pi to 2 decimal places, like that doesn't really count as math. That's something you can ask a computer to do. But it doesn't mean that we stop doing math. And I think that this is sort of a process that has been part of math since its very earliest history. And what we're doing here, and what I see all the other folks doing when they're bringing math and machine learning together, feels much more like a continuation of a process that we've been seeing in math for a long, long time than it seems like a sort of massive disruption that's going to upend the practice of mathematics as we know it. So I'm going to stop there. I know there are questions. Thank you guys so much for coming out in the evening. I really appreciate it.
Well, thank you, Jordan. That was just wonderful, thrilling. We have lots of time for questions. So, okay, yeah.
Hey, Jordan. Thanks a lot. So, from the other DeepMind / Nature paper on using machine learning to progress mathematics, there's this paper by Jordy Williamson where they look at combinatorial invariant. So two things that are really similar amongst your work and that work is that they have essentially an infinite corpus of data to train on, and that one of the big takeaways is that they are inspired by what they can close off from this collaboration between sort of like the machine producing things and their human insights. And I wanted to understand if you
What do you mean by close off? I just want to understand the question. What does that mean?
So in their case,
I know that paper, but I don't know what you mean.
Yeah, in their case, they're looking for subsets of the graph, and they're trying to figure out what might not actually play a role in computing this invariant. In your case, you're trying to understand sort of like what kind of functions might not be good for sort of generating cap sets or generating larger cap sets than you might averagely produce. And so I'm curious, like, does that resonate with what you were trying to get at with your notes and your takeaways?
It does, but I want to say, I mean, maybe I should say I didn't tell this part of the story, but like one thing that happened that I still don't really understand is I had lots of ideas for like, oh, because I know this problem very well, here's some functions that I think the programs should be using, some built-ins that it might not come up with by itself, but that I know is sort of coming from like harmonic analysis or whatever the traditional techniques people use. And much to my disappointment, they did not seem to help. So in some sense, it's hard. So I don't want to make it sound like all of this stuff is automatic success. So in this case, yes, I did have some ideas about kind of nudging it to go in a certain direction that my priors told me would be more productive, and that was not the case, at least in the experiments that we did. But yeah, I mean, I think a big part of this, of closing off, restricting this very restrictive class of programs, I think part of it is not because they decided to do that at the get-go. I think it's because like they were not finding any better results by having taking a broader scope, which is weird. Yeah, in the back.
Can you pop up back to the LLMS? Can do this while you continue to answer questions?
Oh yeah, this one? Okay. Yeah, good, because this is a good takeaway. This is actually one of the big takeaway slides. This is a good one to leave it on.
Yeah, I know you said you think that proofs aren't so important, but
okay, don't tweet that, please.
I just want to add, there are people who actually do try to train large language models to create English language proofs, and then use proof checkers to get the hallucinations out of them and throw away the ones that don't work. It's a lot more complicated than that, and you have to train on mathematical literature, which is a problem because it's not so much and so on. But these people, especially ones working at Elon Musk's company, say they're going to solve the whole thing in the next 2 or 3 years, and I just wanted to get your opinion on that.
Well, I mean, I'll try to stay current on whether they're doing it. No, but I think that's like a really interesting and productive direction. This idea, because this idea of producing something, I think what they're doing is trying to produce formal language proofs so that the assessment step, like here, that part is not LLM. That part is a sort of straightforward formal assessment. If you want to know my opinion, what I think is that, as all the pure mathematicians in the room know, when you're writing a paper, there is a lot of stuff where you're like, okay, I need this lemma. In fact, this was like literally what I was doing this afternoon when you came in. Like, okay, I need this lemma. I know it's right. I don't feel like writing it up. I know it's correct. But like to actually like write down the proof is like sort of annoying. Now, how do we know this? I don't know, yet we're usually right. And I could imagine some world in which just as like now, if I needed to sort of like, compute the ideal generated by some set of polynomials, right? Which I think David likes to do. I'd be like, oh, I could do this, but I'm going to ask Macaulay too to do it, right? I don't think it's that implausible that there will be a world in which the lemmas that are kind of, we somehow sort of know are correct, but it would actually be sort of hard to like, or time consuming or something, sort of like write down the proof properly, that's sort of, oh, bop, give me a formal proof of this. Now I know it's right, so now I'll write it is clear. But secretly, or whatever. Instead of just writing it is clear, which is like what people usually do in their math papers. Sorry for the students, I'm not supposed to say that we do that. But okay, so, but that's different, right? From just being like, oh, I have this big problem that requires major new ideas, and I just ask the machine to do it, which I know there's people who think that's on the horizon. I can't prove to you that it's not. I'm just saying I'm not seeing anything that makes it feel like that's on the horizon. And I guess that's this kind of like slightly controversial picture where I'm like, that would not be in the convex hull. Whereas the lemma that I kind of know is true, but like it would be a pain to write down a proof of, is in the convex hull of like stuff that already exists. So I bet, yeah, never say impossible. I'm just, yeah.
Show it for the mic. First of all, thank you. If we continue with this idea that you can like, if you had like some kind of model or machine that you could put in a theorem in it, and it could like tell you if it could provide a proof or tell you if it's true or not. I'm wondering like if you had that, where is the truth coming from? Like, does the model, is it some intrinsic property of like the machine that produces that truth, or does it already exist? Like, as you said, was it in the convex hull already, or is the computer somehow discovering something new?
Well, let me answer that question with a question. When I asked my calculator to multiply two 30-digit numbers, where is the truth of that computation coming from?
Maybe we already, if it's 2 + 2 + 4, you might already know that's true. But what if it was some new theorem that no one knows if it's true or not?
Yeah, what if it was two 30-digit numbers that have never been multiplied before? That seems rather likely, actually, if I chose them randomly. I think those questions are very similar, and I'm not asking that to dismiss it. I'm actually saying I think both questions sort of have philosophical import, but I don't know. I don't have a clear answer in my own mind. Yeah.
Thank you for the talk. As you looked at the generalization challenge across different values of n, did you explore with the DeepMind team looking at cross-validating to say, let me try and one value of n, and then as you think about selecting the subset to sort of reproduce in the next generation, you explicitly select for the ones that do seem to cross-validate, or they seem to generalize to other values of n. Was that a strategy that you've tried or think might have mileage?
We didn't do it in this project. I have a grad student who, like, not using LLMs, but using more traditional machine learning methods, is sort of trying to build in something like that for sort of other kinds of combinatorial problems. And you know what? It's really hard, actually. It's not clear it's working, but he's working on it quite hard. I mean, I'll say, but this actually gives me the opportunity to say something I didn't get to say, which is that, in some sense, working with DeepMind, this is sort of some smallish set of like highly paid people, and like you got to talk to them every week, but like every time I talk about this stuff, people are like, did you try this? Did you try that? Did you try this? And I'm like, oh, well, we had our weekly meetings and we tried what we tried. But my goal for this, you guys, is in the end, for this to become a meaningful part of mathematical practice, which I hope I've sort of at least made the case that it at least potentially could be. I mean, it has to not go through the bottleneck of like asking DeepMind or somebody else to like, you know, it can't always go through them. We can't always be like, would you mind like, you know, burning down a couple of Ecuadorian rainforests to like solve this problem for me? Like, no, we have to have like lighter versions that we can use ourselves, because then, right, then every mathematician with their own problem can just like, if they have the idea to try something, they can just try it. And that's where I would like us to get.
Thank you.
Sorry, that was not really that was more than an answer to your question. They just gave me the opportunity to say something else I wanted to say.
On the idea of convex hull, I feel like in the history of science and math, I guess in particular, like ideas which are outside of the previous convex hull will often come from some new technological development or some other kind of social development or new encounter with a new aspect of reality. I'm curious, well, I don't know if you could speak on what you think might be things that might be outside of the current convex hull of mathematics, or how machine learning can aid in the discovery of points which are outside of the current convex hull.
Well, let me say this about that. So the question is like, what do I think we can do to sort of like get more extrapolation and get it outside the convex hull? I do want to emphasize that, you know, the way some people would put it is like, well, machine learning is like bad at thinking outside the box. It's good at thinking inside the box. But you know what? It's a big box. And most of it we haven't looked at. So I want to emphasize that I actually think there's like a huge amount of value in searching inside that convex hull, because like, okay, so to be like, right, if you guys know, I know Lisa likes high dimensional statistics, right? Like a very high dimensional box, there's like tons of room in there. And if you've only seen the corners, you haven't seen much. So I think that that's kind of a tall order to be like, how can we really make it extrapolate? And again, maybe this is like the difference between me and the folks who are like, let's overthrow the entire practice of mathematics. I'm not so interested in that for obvious reasons, but I am interested in just sort of like generating productive tools that we can use. And for that, I think these more modest goals are like extremely valuable. Finding, you know, searching the stuff inside the box in a sort of weird, fast, and eccentric way that it doesn't occur to us to do, and like giving us new ideas. Like that's what I'm trying to do.
Anybody else? So I really like your ending line about, you know, like this is a continuation of technology. And it reminds me, there was a speaker here, Alison Gopnik, in a workshop on neuroscience and psychology, and she was listing LLMs as the end of, so not the end, the current. So she was saying people used to talk to each other, then they looked at pictures, then they had written language, then they had printing, then they had Wikipedia, and now they have LLMs. So there was a progression. So this is one more tool to access information. And I think that's a helpful way to think about tools of mathematics, that this is one more tool, and the question is how to use it. You know, rather than to think that there's some new way to get rid of mathematicians or something. But really, the challenge is how to use it to get more than just look up facts or, yeah. I really liked your punchline.
Especially since it's kind of bad at looking up facts. I mean, I think we're trying to find things that it's better at than looking up facts where it might make up some of the facts.
Well, I don't know.
There's no one else. I have something. I like this thing with the box, of course, and I think maybe you can give a thought about which has nothing to do with mathematics, which is human creativity. We always think creativity is so, you know, finding something totally new. But if you go into a jazz club and watch people play, you know, solos in the style of Charlie Parker or Miles Davis, they're doing exactly that. They're in a box, and they are very good at finding new corners in that box, but they don't go outside that box. We shouldn't downplay that, right? If everybody would go outside the box all the time, it would be total chaos, and no one would appreciate anything anymore, because
I've seen some of those jazz shows too, actually.
Yeah, they did. Every 20 years you can have someone.
Yeah, so maybe it's worth saying. I mean, one reason I use the examples that I did is, I don't know if everybody knows this, but I was a novelist before I went back and got my PhD and became a mathematician. So I'm definitely very interested in kind of like what prose fiction produced by an LLM looks like. And actually, I think it's interesting like how bad it is. I don't think it has to be quite as bad as it is, because I think inside the box of the traditional prose novel, there's certainly lots of room in there. And somehow, even with all that room, I think so far that the prose outputted by LLMs there's something wrong with it that I find rather hard to articulate. And I think it's an interesting.
Give it some time.
I mean, I mean, maybe I can't say impossible, but I also can't say it's improving.
I do have a question. I'm not really sure I understand the limitations of the box, so I'll give a question about an example you gave, which is AlphaGo. So the original AlphaGo, which beat that guy, was trained on human players, and then they made another AlphaGo where they deprived
AlphaZero, yeah.
They deprived it of human knowledge and let it learn playing itself, and it beats the other AlphaGo. So is that new thing like in the convex hull, or is that something new that it did? I don't even know where to put it.
So I put the word convex hull in quotes for a reason, because I don't want us to sort of take it too seriously. I think that's actually like one of the most interesting examples, because in some sense, there's some sense in which the process of playing Go is not that different from the process of multiplying large integers together. Feels different, but in some sense, there is an answer to what's the value of each Go position, right? I mean, it's a finite game that has finite rules. It's a computation too large to do, but it's a deterministic answer, right? Each position is either a win or a loss, or a draw, I guess, in Go. So, if you imagine some oracle that just like correctly assigned that position, that score to each position in the game, would you say that was like an outside the box species of creativity, or would you just say it's like a computation, like multiplying numbers together that are too big for any actual computer to multiply?
Well, part of the way we get these things to be more creative is adding randomness to them, right? So think about doing some non-convex optimization, right? You get stuck in a local minimum, so you just throw in some noise and maybe you get to a better one. Maybe that's all. I can't say if that's what people are doing when we call ourselves more creative. Maybe we're just more random. I don't know, but I certainly.
Something from that. Okay.
Thanks. I thought I saw that you'd applied this to bin packing, and maybe that's one of the things you had to cut out, but I was wondering if you could summarize different lessons, same lessons. Yeah.
I can't, and I'll explain why, because the bin packing part of that paper is a part I did not touch. So, I mean, there was two problems of a somewhat simple in nature, which we applied the fun search protocol to, but I was really on the capset side and not on the bin packing side at all. So sorry, that's why.
Thanks. So you mentioned that you tried to learn from the Python programs that were generated, and that was kind of hard, but I'm guessing also there has to be a better way than using Python for those things, because I mean, it might not be the best language to generalize from. I'm guessing there's a trade-off between that and the amount of data available to train, but
yeah.
Has there anything else been tried?
I think that's exactly right. I think the reason that they're doing it in Python is because there is lots of Python, and so they have like a code generating LLM that's trained on Python that works really well. I think there are interesting questions. Okay, now I'm a little bit out over my skis, and so probably people who know this better than me, but my sense is that, for instance, if you try to train an LLM to produce text in a sort of language with fewer speakers, where there's not as much text, if you sort of exclusively train on stuff in that language, you do pretty bad. If you train on like the trillions of English tokens you have, plus stuff in that language, and then prompt in that language, you do much better than if you train in that language alone. Like there's enough commonality so that you actually get some extra oomph. So it's possible, you can imagine a situation, we didn't do it, but if you think some other language is superior, you could imagine training on like a lot of Python and some of that, and then prompting it to generate, Julia or APL or like whatever the hell you want. We didn't try that, but you could. And again, I have no intuition for whether to expect that to work better or worse. For a number of theorists like me, I work in a very old area where we have a lot of heuristics and a lot of intuitions. It's kind of simultaneously like, disorienting and nauseating, but also exciting to like work in an area where like nobody has any intuitions for what's going to work. You just try stuff.
Yes.
You said that it's not good at like combining the small dimension solutions, but is it possible to inject that kind of bias to generate some better thing?
I think that would be cool. We don't quite know how to do it. I think there was maybe some sense that, maybe in the kind of AlphaZero style, we wanted to like not cheat as much as we could, right? Sort of like there was some feeling of like, well, maybe we don't want to kind of give it like too much of what we know about the problem, like knowing that. Well, I say that, but I mean, in some sense, one of the directions I didn't talk about was certainly using material that other people did on this problem, like the humans did, and then kind of like building on top of that. I don't know. So basically, I don't know. I don't know how to get it to do this without sort of like building it in. And maybe building it in is cheating. I mean, I think the idea of somehow gently suggesting it is interesting, but I don't know how to do it.
So I'm curious how much of cherry picking it was to focus on capset and bin packing, because you said even like excluding out of distribution generalization, it's very easy to cook up failure modes where this 10 to the 6 and then try to refine that would be like completely pointless, right? So presumably there are like cases you tried which failed and problems you tried. Could you talk a bit about that?
I would actually say it's the opposite of cherry picking in the sense that, and this is also another difference between the sort of academic mindset and the industry mindset is, I would actually, I mean, capset is like a sort of famous old problem that people have worked on pretty hard. To me, there's much more to be gained from working on problems that people have not worked on that hard, because that's where you're more likely to get some juice from the machine. But I think if you're DeepMind, it's somehow more interesting to work on high prestige problems where you can say like we beat state of the art on like famous problems that people have worked on a lot. So yeah, I mean, so. But when you say were there failures, you don't mean for this problem. You mean were there other problems we tried and got nothing?
LLMs themselves have failure modes that they learn completely nothing in distribution, right? So that's not exactly fixing just with the fun search idea.
Well, so maybe a good example is, why is this problem about Shannon capacity in the supplemental materials and like not in the main body of the paper? Because there's no case in which like we beat the best known independent set in the strong power, whatever. There's sort of no case in which you beat human state of the art. And yet, as I tried to convey, the result that was like most exciting to me personally was in that part of the project. But yeah, I think like inevitably, and I mean, maybe I should say, so somebody mentioned Jordi. So I mean, I'm working with Jordi and Adam Wagner and Francois Charton and like sort of just a whole bunch of kind of transformery approaches to like a bunch of different problems, just to try to get a sense of like, where is it going to get results and where not. And like, mostly it does not. I don't want to lie about that. It's not like magic. But we're just at such the beginning of the subject that we're sort of probably eventually we'll have some kind of intuition on which types of problems are more amenable, but right now we don't. So we got to develop it.
We have time for maybe one last question.
I had a question specific to capset, which is the solution for n equals 8. Was that the only program achieving 512, or did it find like hundreds of programs that achieve 512? And if there were multiple, is it the same capset that it produces?
Oh, that's an awesome question. I think for that there was only one, but I am truly not sure. And I think for the smaller ones, there were multiple programs that generated the same thing. And then it's actually sort of some amount of work. Certainly the programs didn't look the same, but they might be generating the same capset or ones which were isomorphic. So, and when that happens, by the way, I don't know if this is valid or not, but it makes you feel like, okay, that's probably actually biggest. If it's somehow hitting the same thing like multiple times and not getting past it, it makes you feel like, okay, maybe there's some actual wall there where the reason you can't go bigger is because there isn't one bigger. But of course, that's not a proof.
Okay, well, thank you, Jordan, and yeah, let's thank Jordan again.
Thank you so much.